Welcome to breadboarding. This is part 4 of video 13 in the breadboard video controller series, and in this video we're going to be finishing off the 256 color graphics option on the video controller and see if we can display the Doom startup screen. So this is finishing off step 7 of the video controller plan. We've already done number 8 in some of the earlier videos. In part 3 we finished off doing the hardware installation for these last 3 items: the video digital analog converter, color multiplexer and an additional latch. So that's all been installed in the previous video, and now we're going to go on and do testing of the video mode, initially just with character mode to make sure that the way we installed the digital analog converter hasn't broken anything. Then I'm going to be covering a couple of the issues I had to debug with this new mode. I'll talk about that in a minute. Then looking a bit at the Doom test image. So this is a 256 color image of the same resolution as the video mode that we're using here. Then we're going to cover a utility that will convert that PNG format image into the S-record format that Nanocomp can download straight down into video memory. We'll do some basic testing of the 256 color mode. Then we'll start to load the Doom test image, and then once we've fixed some of the color palette issues, we should end up with the full 256 color Doom image then being displayed on the video controller. And that will lead us to the conclusion of the breadboard video controller series, and we'll start to look at other stages of the project to complete the Nanocomp. I have already run this a little bit before, and there were 2 mistakes that I found. One was that the address lines on the parallel interface adapter chip that I was taking the A0 and A1 lines off were reversed on the original design, because that's the way how the original Nanocomp was done, so I had to reverse that. And I also found out that the rules for my read and write signals for the video DAC weren't quite right, so they need to be reversed. So I've done those minor changes, and we're just now going to turn on the Nanocomp. So this is now getting the color signals through the video DAC, but when it turns on you can see that we've only really got black and white at the moment. So what I'm just going to do now is to download the test program. So here's a test program. It's very simple at the moment. All I'm doing is calling a palette initialization procedure and then a palette test procedure, and these routines are in the Nanocomp shared sort of library. The palette init basically reads through the default palette which I've loaded from another source. So this array here has the default palette, which is the same as the standard VGA palette, and then basically what this initialization does is read through that array, sets the index for the palette, and then sets the red, green, blue values, and then reads it back and outputs that to the debug console. And then the test basically just reads everything back. And what I was doing originally was comparing the red value with the default palette value and then outputting it, but I've just chosen to comment out those bits so it'll actually print out all of the values every time. So we're just going to compile that, and then we just need to download it onto the Nanocomp. So this is the srec file, so I'll just put it in load, send file. Okay, so that's ready to go now. So we'll just go back to the screen share. Right, so you can see at the moment we've got the just black and white at the moment, which seems to be the default for the video DAC when it initializes. What we'd expect this to do now is we by default have white in the foreground, blue in the background for the Nanocomp, and the first 16 colors should be the same as the original Nanocomp hardwired colors. So if you just run this now, and we will capture the output as well. So we're capturing the output. So just run this. Okay, so you can see it's now giving us a blue output, which is what we'd expect. And if we just skip back to the screen share here, and we'll have a look at the file capture from the terminal, and you can see here that what we've got is for each of the indexes we've got the different values, and in fact when it reads the address after the third value is written, the address increments in fact. So all this is showing is that we write address 0, and in the accessing the current address here, it's actually already moved on to the next address, because the when you read or write the last color value of the 3 color values, it automatically increments the address. So that's the initialization. So we have about 255 values there, and then this is the test where we're really reading it. Now generally the mismatch here is just because I've commented out the condition for the mismatch, but this just basically shows that we're able to read back all of the video DAC values. So the 2 problems I had really was the read and write signals, the logic for it had got reversed, and the fact that I was using the reversed A0, A1 signals, which drive the parallel interface adapter because of the way how the original memory map was done. So now that those are working okay, what I'm just going to do now is to send down one of the test programs that I've used previously. So this is a CRT6 test program, which is from one of the earlier videos, and what this does is just outputs the character set and the 16 colors down the bottom of the screen. So that's ready to run. So we're just going to go back to the capture card. Okay, and if I just run this, we should now get a screen there. So you can see that down the bottom on row 21 there, we've got black, grey, blue, slightly different shade of blue, the greens. So those are all the colours we'd expect. Now the only issue is in character based mode we can only do the base 16 colours, because the character mode only allows us to have 16 foreground and 16 background colours at the moment. So what I'm going to do now is to get the high color graphics mode running. We're going to get a test program to see if we can output different colors in the graphics mode. I suspect there'll be some more debugging to do here, because I haven't run the high color graphics mode successfully yet, so we'll come back once we've done that. So this is the finished high color video card. There is a bit of mess around here in that in debugging it I needed to add a delay to 2 of the clock signals that we're using to drive the A0, A1 address lines for the video chips. So what this basically does is adds a delay of about 80 nanoseconds to 2 of those signals, and I'll just explain how I came across that. So this is an output from my logic analyzer, and what this is basically showing is I'm looking at the input values going into the video DAC. So this is the D0 to D7 lines going into the digital analog converter, and what I'm looking to try and do is to understand why some of the data wasn't coming out quite right at the top of the screen. And so what I was looking for was the video sync here. So this is the video sync for each page, and basically our output here arrives about 29 horizontal line sync signals after the end of the video sync. And what we can also do is use the timing markers here and the pulse counter here. So this pulse counter is saying how many pulses were there between A1 and A2, and that's really how we found this out. And what that basically allowed me to do is using 2 of the logic analyzers, one looking at the data and the other looking at the address timing signals. So this is then showing the more detailed view, and this is looking at the QB, QC, row address 1, memory address 1, memory address 2. So these are the signals driving the video RAM from the CRTC. And what I was able to do here is then to find out where the video sync was here. This is the horizontal sync, and then basically they were able to find whereabouts the video DAC signals were coming. And then this is drilling down further, and we can see here where this line is where the higher level address lines go back to 0. So this is really at the beginning of the screen. And at the top here we can see that the QB and QC values, which are the clock signals that give us the 4 dots within each character cell, that we're decoding that, and we can see that in fact when all these other CRT signals go low, that we're actually starting at 0, 0, 1, 0, 0, 2, 0, 0, 3, and in fact 0, 0 appears almost in the next cell. We can see here that the value here actually changes after this. And what this was basically resulting in is the pixel that I would expect to appear on the left here was appearing on the right, which is quite confusing. So what's happening is that because the relative timing of the QB/QC signals that come really straight from dividing the dot clock with the output from the CRTC, there is a bit of a lag from the CRTC. So what we actually need to do is, this is the 00 value here that we need to appearing here. So what I end up doing is adding a delay of QA clock cycle, which is the dot clock divided by 2 signal, and what that will do is to shift this 00 value to here, and then 3 will in fact be appearing here. So that's what I need to do to fix that problem. It took me quite a while to get to the bottom of this. And then this is output from the logic analyzer once it's fixed, being put in. So you can see here, this line here is where the CRTC is changing the values back to start at the top of the screen. And you can now see that rather than starting at 01, we're now starting at 00, and it's also ending at 03 before it goes on to the next one. So this particular problem took me quite a long time to get to the bottom of. It's a fairly simple fix, just needed to add 2 flip-flops clocked by the QA signal, and that was all that was necessary. So what we're going to do now is to show you the test program that I've used for doing this, and also then how we're going to output the Doom start screen logo out to the video controller. So I'm just going to show you the Doom image that we're going to try and display on the video controller. So I'll just make this a bit bigger. And if we just have a look at the file properties, we can see that this is 320 pixels across, 200 down, and it's got 8-bit color. And this is a PNG, portable network graphic file format, and this appeared to be the simplest graphics file format to work with. The GIF file format is a bit older and probably from around that sort of era, but was a bit more difficult to get libraries that would actually interact with it. So what we need to do is to take the image here, which includes both palette information and also the image 320 by 200 pixel information, and we need to take that and actually put it into an SREC format that we can then use to download to the Nanocomp. And what I'm going to do is to load this directly into the Nanocomp video memory, so we don't have to store it anywhere, because this file is actually too big to fit in the Nanocomp memory, and there's no way we could actually extract the PNG file and put it into the video memory on the current Nanocomp as it stands. So there's a third-party library, libspng, which I've used for this, so thanks to Randy who's provided this, and all I've done with that is downloaded it, and there is a example program which I've used as the basis for modifying this. So if you look at the win merge for the example here, and this is just going to go through and show what the different changes are. So minor changes, I've included the Nanocomp library because there's some memory details and things in there. Basically this example shows how to read a PNG file and to manipulate it, in particular getting the palette information out. So this code I've got here is taking the palette entries and outputting them as an SREC format. So you can see here we've got the code here necessary to calculate the checksums for the sRecord format, and it just outputs the details in hex. Then we needed to comment out some of the options in here, and outputting the image size just for information purposes, and you'll see this in the output file. Commenting in doing the image in one go, and the default example allows you to pass the image in chunks. And then basically this is the code that I've had to add, and what we're basically doing is having to take the image and divide it up into the way how the video RAM works. Now if you remember when we were looking at the address mapping for the video RAM, that because of the limitations of the 6845 CRTC for being able to address the amount of RAM we need to do the graphics modes, that in fact we're making use of the QA QB clock signals and also the row address 1. And what that means is that in fact when we're doing the first 4 pixels, that will go from 8000 to 8003, but then the next 4 pixels will actually be on the line below. So effectively we do 4 pixels on the first line, then 4 pixels, and we zigzag up and down. So as we actually pass the PNG data, what we've got to do is to process 2 lines at a time and output the data to the srec file in this sort of sequence. Otherwise we're going to get something coming out quite garbled. Now this makes it a little bit more difficult to program, but it makes the hardware design a little bit simpler. And perhaps when they come to look at recreating PC compatible video cards, perhaps in the future we may need to change the way how this video map works, but it certainly makes things easier than it would be if we were dealing with multiple planes of memory. So as we go through and we read the image, what I've actually done here is got 2 pointers to the first row and then the second row. And what this basically does is maintains the srec checksum and outputs the video RAM address, and then as it goes through 640 bytes at a time, it basically does chunks of 16 bytes at a time, but it's actually using 4 bytes from the first row, 4 bytes from the second row, 4 bytes from the first row, 4 bytes from the second row, and then outputs the checksum and does some checks to see if we've got to the end of the video page. And basically what this does is outputs an srec file that we can just load straight into the video RAM, because it also includes the necessary address to set the video mode as well. And what I'll do is I'll run this and we can then see how this works. Okay, so let's compile this. So there's a few warnings there, but it doesn't really matter too much. There's a few things here. I didn't really need to clear this up too much. Then what we want to do is to output this. So we're going to run the program. We're reading in the Doom.png file, and we're going to output to an srec file. We'll just call this srec value. Okay, so that's run without any problems. If we go into our text editor, and we'll now find the Doom.srec file. So you'll see here that I've included some of the information that the example program did, so we do need to tidy this srec file up a little bit. So you can see here we've got the width, height, bit depth, and because this has got palette information included in it. So what I'm just going to do is get rid of this information here. And because this has carriage return line feed data in it, what I'm going to do is just replace all the carriage returns and strip those out. And the easiest way to do that is just to replace them with nothing. Okay, so that's got rid of the carriage returns. So what we've got here, from 4000 hex, I'm actually loading the palette information for this particular PNG file. Now the only issue I did have as well with this is that the values for the PNG values are 0 to 255, and in fact our video DAC only uses 0 to 63. So what I did have to do is to modify the code here slightly to only take the most significant 6 bits. So effectively I rotated the current value right by 2 bit values, and so this value is an adjusted value that will suit the video DAC. So then we've got the message there for the length of the file, so it's 64,000 bytes, and so just get rid of that. And then this first entry here, this is actually the page register address, and what we're doing is setting this to our high color graphics mode page address 0, and then we'll then find, if we search for this particular address, then find that after we've done 800 to BFFF, we then get the next page, so that's 0D, so that's page 1, this is page 2, page 3, so 0F would be page 3 of the video RAM, and then finally when we get to the end, got a few of these values appearing in the, finally when we get to the end, we're just going to output 0C to set it back. And in fact, there's one extra thing we do need to worry about in here, which I don't think has actually come out in the code. We just need to make sure that there is the S9 end of file srec. So what I'm going to do is just find another S record that I've got here. See here, we've got a S9 end of file record, so we're just going to chuck that in on the end. Okay, so what we've now got here is our Doom.srec file. If we load this into the Nanocomp when it's set up for running in the high color graphics mode, this will first of all download the palette information. Now, to start with, the image won't look right because until we've actually run a program to copy this palette information into the video DAC, then the color mapping won't be correct, and so it'll look a bit odd the first time. But the second time we download the image, you'll then see that it will come out to be a lot better. So in order to test this out, what I've got is a simple test program I've done here, and you can see here that we're using the serial console out hook for the CMOC environment here. I've got some code here to initialize the palette information, and in fact now what I've done is added a CRTC init code to our main Nanocomp routines here. So what this CRTC init does will actually set the CRTC page register values. So this is a 6845 values. So this first one here is text mode 80 by 30. The next one here is 80 by 25 at 70 Hertz. Then we've got our 640 by 480 at about 60 Hertz, which is the one we use for the Lander game. And then this is graphics video mode 3. So I call it graphics mode video mode 3. We've then got the 320 by 200 based on the 70 Hertz 80 by 25 values. But this does actually have to have different values in here. In particular, we have got the number of lines per character is set at 4, so we've effectively got 4 lines per character cell, and because we've got 100 columns or rows down, then we've got 400 lines in total. And what we're actually doing, as we discussed in earlier videos, we're ignoring the row address raster address 0 line. We're only picking up raster address 1, so it basically means that we've got each line will be doubled up, so we get 200 lines. So if we go back to the test program, there's a very simple color test here that all I'm doing is outputting sequential bytes to the screen just to check to see if what's going on here. And there's some code here which I've copied out and put into some other versions, which actually copies the memory with the palette from the Doom image and copies it into the palette DAC registers. But so this particular one, we're just going to run this up on the Nanocomp, and we'll just check to see that the basic video 256 colors is working, and then we'll have a go at loading the Doom image. Monitor startup message. So you can see here at the moment we've just got black and white at the moment because the video DAC has not been initialized with any values. We'll see if we do reset a little bit later that we'll probably have the white on blue. So what I'm going to do first of all is to load up the test program. So here's the test program, I'm just going to send that down. And this will output some diagnostic messages to the display here, which we can come back and have a look if we need to. So let's go back to the video capture card. So this is not a very exciting test program, but it will just allow me to test that the video mode is working. So if you just run this, and it's actually taking a little while to blank out the video RAM, and you can see at the top here there's a basic sort of a test palette here. So this is outputting the 256 palette values, very, very small. I'll rewrite this at some point in time and make it larger blocks, perhaps with some numeric values to show which palette color is which value, but it's sufficient to allow us to verify that it's working okay. And what I'm now going to do is to load our Doom.srec file first of all. Now, to start with, it won't look great because the video palette information will have not been set. So I'm just now going to switch back to our screen share. We're now going to find the Doom.srec file. So I'm just going to send this. If we switch back to our video capture, you should actually be able to see the data being loaded. So this is going down the serial port from the PC to the Nanocomp and then going directly into the video RAM. So you should actually see this updating as we go along. So I'm just going to start sending that now. So it does the video palette first, and then this is now the Doom image coming through, but as you can see, the colours aren't quite right at this point in time. But once we run the test program that I've got, I think it's test program 3, and what this does is copies the area of memory where the palette information is being loaded and copies that into the video DAC. So it looks a bit strange at the moment, but once we load it the second time, then we'll find it all comes out quite nicely. Okay, so that's just about done. So that's actually downloading, I think it was about 170k of S-record format. Okay, so that's the whole image, but because we haven't actually initialized the palette for the video DAC yet, it's not going to look great. So I'm just going to do that now. So here's the simple test program just for copying the Doom images palette information into the video DAC. So basically the S-record file copies the palette information to memory starting at 4000. So if we have a look at the Doom srec file there, you can see that all the palette information, the 3 byte values, red, green, blue values, start at 4000 and go down to what about 42CA. So basically all this program does is to take the red, green, blue values and actually output the palette address byte in a loop going from, I think it's 0 to 239, the number of palette values that were in there. So this is just going to take those values and output it. It does also do a CRTC in it just in case anything else will be messing around. So that will actually clear the screen as part of that. But what it will mean is because the palette will be initialized correctly, when we load the Doom image again, it should come through and look pretty much perfect for when it comes through. So let's just download that program into the Nanocomp. I compiled it earlier. So this is the test program 3. Once that's downloaded, we'll just go back to our video capture. So you can see this is the one we downloaded, but that means that the palette information is now in the RAM starting at 4000. So we now just need to, so now going to run that test 3 program, and that is going to clear the screen, but it's also going to initialize the palette information. So all I need to do now is I'm just going to download the Doom.srec file again, and what we should now see is the image come through, which hopefully should have the correct colors. So I'm just going to start sending that now. So you can see now it's sort of building up the image sort of one row at a time, and the color information is much better, and it should pretty much match our original Doom image completely. There is still a little bit of interference as we're updating the video RAM, and that's one of the things I will look in the future, particularly once we've speeded up the processor, is see whether or not we can arrange the memory update such that it doesn't cause the interference during video RAM updates. And the speed of this is primarily the speed of the serial communications downloading the S-record file. You can obviously update the screen a bit faster than this. So there it is. We've managed to get the Nanocomp with the breadboard video controller to be able to load a Doom startup screen image, which is 320 pixels across by 200 down and 256 color palette. And this was the video resolution that was used on a lot of the PC DOS games, and is typically the one that was used for everything until we started to get Windows and all of the video accelerator cards and things like that. So unfortunately the Nanocomp on the 6809 running about 1 megahertz is nowhere near fast enough to be able to run Doom, but it can show the Doom screen. So thanks for watching. If you found it interesting, please hit subscribe, and if you found the content useful, please hit like as well. In the future videos, I'm going to be having a look at adding a PS2 keyboard to the Nanocomp. I may also have a look at whether or not I can access IDE hard drives, or perhaps an SD card in an IDE converter, to see whether or not it's practical to be able to access hard disks from the 6809 computer. Thanks for watching.